Okay, perfect. So today I will be talking about single slot finality. So this is a longer term proposal for where Ethereum proof of stake could go. So longer term than Virtual trees, longer term than dank sharding, longer term than any of the stuff that's like under active development. And the core idea here is single slot finality, right? So basically make it so that instead of blocks finalizing after like 2 epochs, after some period of time that is currently around 13 minutes, finalize blocks after one single slot. And we'll talk about like why this might be better, why this might be simpler, why this might lead to a protocol that has less bugs in it, and why it could actually be like computationally viable when I think historically we haven't really thought of it as being computationally viable. So to start off, just a bit of background about like where we are today and why we are where we are today. So in 2017, I published this article, Parameterizing Casper, the Decentralization Finality Time Overhead Trade-off, where I basically talked about like these 3 different axes that are good properties for a consensus algorithm in a blockchain to have. So one of them is low time to finality. The other is a large validator set. And the third is low node overhead. So low time to finality, lots of reasons why it's good. It's good UX, but also on top of that, like we've recently been worrying more about like MEV related reorg attacks, all kinds of other attacks, and having a chain that just finalizes instantly basically makes an entire class of issues go away. Large validator set needed to make it possible for regular people to be able to stake. So it's a kind of decentralization, and low node overhead, also another kind of decentralization. And the argument was that, well, there's actually a pretty simple mathematical reason why you can't have all 3 at the same time. And the argument is basically that, like, well, finalizing actually requires every validator to send a message once, right? Like all of these BFT algorithms, they require 2 rounds of messaging, and in each of these rounds, every single validator needs to send 1 message, right? So, you know, if you're familiar with how Tendermint works or how like traditional BFT algorithms work, you know, round 1, someone proposes, everyone makes a pre-commit. Round 2, everyone makes a commit, and then if you look at how Casper works, it's basically the same thing except spread out over 64 slots. And if you look at algorithms that don't have this kind of high overhead of a lot of messages, they generally don't finalize, right? So if you look at chain-based proof of stake, so like, you know, Peercoin, Next, Tezos, Cardano, like that whole family, they just basically don't have the same concept of economic finality. They just have either 1 or a few messages per slot, and so they can have a large validator set, they can have low time to overhead, but time to finality basically shoots up toward infinity. And like they don't even bother to code economic finality of any kind. The most BFT, like BFT-based non-Ethereum chains that exist today, they tend to sacrifice on this. So node overhead tends to be either low or medium. I mean, realistically, a lot of these chains don't even care about decentralization at all. So like, you know, if you're processing like 400 TPS and you know, your node is a data center already, like, you know, who cares if you're also processing an extra 10,000 ECDSA signatures every second. But they end up like basically sacrificing on more than a very small number of people being able to validate, right? So older chains sacrifice on this, current kind of high capacity chains sacrifice on this, and then some. I don't think there's many chains that like really that only sacrifice on this, because like if you can support, what's the point of supporting 1 million people being able to be validators if being a validator requires a data center that you can't find 1 million people who can afford? But this is kind of the trade-off space where we have today, right? But, and Ethereum like made this interesting choice where basically instead of being extreme, we kind of tried to be somewhere in the middle and like be not too bad on any of the dimensions, right? So like we have finality, but it's not instant finality. You know, we have a large validator set, but like, you know, you still need 32 ETH, which is pretty expensive these days. And we have, you know, fairly low overhead, but, you know, it would be nice if it was lower, and, you know, validating could fit on a phone, but we're not really quite there. So we're kind of in the middle on all three, right? Since 2017, we've, I think, discovered a few things. So one of them, big credit to Justin here for like really pushing this one forward. Basically, with BLS signatures, you can have like aggregate signature verification. So you can compress a huge number of signatures together into an object that is 32 bytes constant size plus 1 bit per participant, right? You just have a bit field of like who participated. And so even if you have 1 million validators, well, the bit field is just 128 kilobytes, right? Which is like basically, a bit more than the size that Ethereum blocks are today. And verifying BLS aggregated signatures per validator is much, much faster than verifying, say, a bunch of ECDSA signatures or a bunch of Shor signatures or a bunch of whatever regular signatures together, right? Because to verify a BLS aggregate, you basically have your signature, then you figure out which public keys participated, you add up those public keys, and then you verify once. And so per public key that participated, instead of needing to do like elliptic curve multiplications, you just need 1 elliptic curve addition, right? So that's, I believe, half a microsecond. So very fast, huge savings on computation, about as much savings on data. So BLS aggregation actually allows us to decrease node overhead by quite a bit without actually sacrificing on the other dimensions, right? Like, so instead of just like picking a different spot on the frontier, we can actually kind of like advance the entire frontier, right? This is, what better technology does. So that's one discovery. Another discovery that I think we've had since 2017 is like a more kind of philosophical discovery, which is that medium finality time, I think, is like less valuable than we think, and specifically having like very low, like minimum possible finality time turned out to be more valuable than we think, right? So there's a couple of different reasons for this. Like one of them is that today, Ethereum does not provide finality, and exchanges are actually still okay recognizing deposits after like a few minutes, right? So exchanges today, lots of them recognize deposits after 5 to 10 minutes. Okay, fine, we have finality after 13 to 15 minutes, but like the non-finality security that we have is probably already good enough, right? And so lots of exchanges are probably just going to like accept that after like maybe 1 to 5 minutes, and lots of services are just not even going to bother with waiting for a finality. Like, okay, we have this thing, transactions can't be reverted, but like it takes just a little bit longer than lots of people are comfortable waiting, and so like how many people is it actually going to benefit? Another argument for why single slot finality is like a really significant leap over medium time finality is the issues around MEV and reorgs, right? Basically, the issue is that if a reorg is possible, then there might be situations where, like, let's say there's like a big liquidation event, like, Justin Sun does something stupid on the blockchain, prices go down a bit, and there's like one opportunity to kind of snipe at him and grab $500 million, right? This almost happened. If anyone remembers the history, this was, I think good old coronavirus Black Tuesday back in 2020. Basically, the problem is like, okay, Justin Sun gets sniped, someone lucky wins, $100 million or whatever, but then you've created a really huge incentive for people to reorg the chain, right? And basically try to like re-snipe and grab that opportunity for themselves. And the problem is that like there isn't a huge disincentive against doing this. There's like informal disincentives, like, oh, if you do this, then people might trust Ethereum less, and if you're a validator, you hold ETH and blah, blah, blah. But like there isn't this kind of ironclad incentive that we have for like, say, slashing against if you break finality. And the thing that single slot finality gives you is it gives you this property that even after a single slot, like basically as soon as block n is confirmed, like even before the contents of block n+1 actually even need to get committed to, basically you're already finalized, and so there's no way to actually, like for the validator set to then decide to take that back in reorg, right? Which is really nice. Now, I mean, it's not perfect because, well, technically, if the validator set wants to really be mean, they could just decide to, not find, like, take half their nodes offline and like make a non-finalizing chain for a bit, but like the cost of it to them of doing that still becomes quite a bit higher. Right? So basically low finality time has these like extra really nice benefits, and so there just really are nice gains in going all the way. Another discovery since 2017 is that, well, this kind of awkward middle ground that we've invented, like, it's awkward and there's lots of places in there that could have bugs, right? So there's this bug from Ryuya Nakamura back from 2019, the decoy flip-flop that really took advantage of kind of misalignment between LMD Ghost and FFG. There's also been some recent bugs that we've resolved over the last few months that have to do with the LMD Ghost mechanism by itself. So, you know, lots of kind of potential skeletons in the closet of this stuff. And if we, like, basically just move away from this sort of thing entirely, then, like, that entire class of bugs just disappears, right? So the question is, can we make Ethereum finalize in one slot? Now, we can do the math, right? So let's suppose that we have 1 million validators. So suppose we have 32 million staked ETH. Now, every node has to vote twice per finality round. Let's say we increase the slot time to 16 seconds, you know, finally have powers of 2 everywhere. Then every node has to vote twice per finality round, so every node has to vote once per 8 seconds. So that's 125,000 signatures per second. With BLS aggregation, if you just want a node that's verifying the chain, the marginal cost of verifying one signature, so if in an aggregate is 1 elliptic curve addition, half a microsecond, and so validating a block that contains a size 125 aggregate is going to be half a microsecond times 125K, which is 62 milliseconds, which is like well within the bounds of tolerance, right? So if you just kind of look at the naive math, it seems like, you know, we can do this. Now, if we want to like push the overhead down even further, there's this interesting trade-off opportunity, which is this idea of supercommittees, right? So I did this informal poll of like basically like how much actual kind of minimum cost of attacking Ethereum, like how much money being slashed from Ethereum being attacked do we really need to be comfortable with? And like, you know, the kind of median of people's wishes seems to be somewhere between 1 and 2 million ETH. So what if we say, okay, fine, like that's, like we don't try to provide, you know, 10 million ETH of anti-slashing security because that's overhead, because that's overkill. And let's say, you know, even if the validator set is really big, keep slashing security to like 1 to 2 million ETH. A committee of size 4 million is, so 125K validators would achieve a cost of attack of 1.3 million ETH, right? And so what you do is you basically say, no matter how big the validator set is, take a super committee of size 125K, choose it randomly, adjust it by a few percent every time there's finality, and you only use that to finalize, right? And if we do that, then, you know, we can cut the overhead down even more. This is if we want, right? So if we want to have verification be faster than 62 microseconds, or if we're okay with these numbers and we want to decrease the deposit size from 32 to 4, then like this is also an option. Now, so far I only talked about verifying a block while that block already has all of the aggregates inside of it, right? The main bottleneck so far, from what we know so far, is not actually verifying these BLS signatures once they're already safely inside of a block. It's aggregation, right? So verifying huge BLS aggregates is easy. Actually doing the aggregating is hard, right? And so far we have like less good ways of doing that. So if today we actually had you know, 1 million validators and we made a hard fork, reduced the epoch length from 32 to 1, then the place where things would break first and like, you know, break the most terribly is the aggregation layer. So can we improve the aggregation layer, right? So there's a couple of possible strategies for this. One of them is that we can take the existing approach to aggregation that we have today, and we can kind of improve it incrementally, right? We could have more subnets, so we could have you know, hundreds of different subnets, and aggregation for small pieces happen on the subnets, and then on the main subnet, you just like do a little bit more work. You could have multi-layer aggregation, so instead of 2 steps, we go up to having 3 steps. And We could also basically borrow from the kind of PBS idea, and we can use specialized aggregators. So we can say, well, okay, fine, we're going to rely on this idea that there are some special nodes that have a global view and only a few people run them, but really there's like a one of n trust model, like basically whoever provides the best aggregate wins. And as long as there's one honest node providing super aggregates, we just rely on that, and could even have it in protocol reward for this. Or potentially we could even like just not bother with rewards, right? So there's like this big design space for ways to improve aggregation, but like there's no theoretical reason why aggregation of even size 1 million aggregates needs to be that hard, right? Like there's definitely a kind of structures, tree structures, whatever other structures that can do it in principle. We just have to like solve the hard engineering problem. So that's kind of the technical side of like how to make it scalable. The next question is, well, what would single slot finality look like from a theoretical standpoint, right? So today we have Casper FFG and we have LMD Ghost, and we roughly know the way that those two interact with each other. The really nice property of single slot finality is that in the normal case, so in the case where latency is good, you actually have more than 2/3 online, then basically the fork choice rule does not even need to run, right? The fork choice rule only runs during exceptions, when you have more than 1/3 offline or when network latency is crazy. So in the normal case, you can basically only the BFT algorithm would run, and so in the normal case you can just remove an entire class of attacks that we have to worry about today, right? So for the fork choice, you could use any fork choice. You could use LMD Ghost. You could use like some other like committee longest chain thing. You can use something fancy. We don't really have to care about what it is. And the BFT algorithm that we choose could be more conventional, right? So if we want, we could, quote, just use Tendermint. Now, not Tendermint the software, because like we do want all this BLS aggregation stuff. But we can use this, like if in principle we could use the exact same algorithm. So probably the one challenge of figuring this out is the BFT fork choice interaction layer, which is, I think, a bit simpler here than it is today, because today, they kind of interact on a very deep level with each other, but here the interaction is simpler, and most of the time, only one of them is like actually contributing, and the other is kind of on the sidelines. But the basic idea here is that the fork choice makes suggestions about what the BFT layer should finalize, right? So the way the BFT layer works is usually someone proposes 2/3 pre-commit and then 2/3 commit, right? But then you basically, if you have a fork choice mechanism, then you have this fork choice and someone proposes according to the fork choice, and then the pre-committers only pre-commit if that matches their fork choice, and then they also commit only if that matches their fork choice. So the basic kind of idea behind how the interaction would work, there's like fairly easy options. Now, there are some subtleties, right? So one of the subtleties is the inactivity leak. So the way that this sort of thing actually like manages to survive the case where you have more than 1/3 offline is that you have this leak mechanism, and so the balances of the validators adjust until eventually, like whatever happened at the beginning, at the end, 2/3 actually are online, right? You just leak the offline ones until the percent online goes up to 2/3. But the problem is that that introduces a bit of subtlety, because we don't just have to finalize a block, but we also have to finalize how long it took to finalize the block, because we want to finalize like what these balance changes are. And we also want to finalize the growing non-finalized chain, right? So the way that these BFT algorithms work generally is like sometimes they kind of lock onto a particular value and then they take much longer to finalize it. But then like we don't just want to finalize the thing that we locked onto, because the thing that we locked onto could be a thing from like a week ago. We also want to finalize like, well, everything that happened since then. And that might have to happen during the next round of finality. That like, this is one of the things that we just have to kind of think through, right? So there are easy options, like the easy options are just take the status quo and replace the epoch length with 1. But I think given that, this is a 5-year project, and this, in my opinion, like, we should only do crazy things like this once the high priority crazy things that we need for, scalability and proof of stake and and all of that stuff are done, and people kind of want, breathe a little easier. Like, we do have time during which we can kind of research this properly and figure out like really what the best approach is. So other goodies. So these are like things that are, in my opinion, nice to have for like an ideal proof of stake algorithm. One is one thing I want to like ideally have is like better theory for kind of like better formalized theory for responding to 51% censorship attacks, right? So responding to 51% reversion attacks is easy. Like, people get slashed and you're fine. Responding to censorship attacks, like, what's the best we can do? The best we can do is probably that like validators, make sure that validators who are censored automatically coordinate on a chain that ignores everyone who's censoring them, right? So like in principle, this is the sort of something like this should be possible to do, right? It should be possible to create a system where if a validator notices that they're being censored by a particular chain, then they basically stop even trying to build on that particular chain, and they start trying to kind of build on whatever the whatever the best chain is that actually is being honest toward them. And so try to like automatically create a situation where if there is a censorship attack, then there's like a clear bad guy chain, and then there's also a clear good guy chain as much as possible as well. So like figure out to what extent that is possible, try to like figure out like what that actually looks like is one problem. And ideally, users should be able to like get alerts and see this sort of thing as well, right? Like ideally, response to censorship attacks should be kind of as close to just like users seeing, a warning and having to decide like whether or not to press a button as possible. Then other things. So better treatment of entry and exit queues. Can we have entry and exit queues that happen faster? Partial deposits, partial withdrawals. Lots of people want this. Variable balances. Like one of the nice things about dank sharding actually is that I think is being kind of a bit understated is that with dank sharding, we basically almost don't need committees anymore, right? Because originally the committees were there because we had 64 shards. With dank sharding, we don't really have a concept of shards in this to the same extent. Like we have sharding, but it's kind of like more fluid and like everyone verifies a little bit of everything. And the only reason we have committees for today is because, or post dank sharding, is because we have to split the validator set into 32 pieces and assign like 1/32 of the validator slot to each a validator set to each slot, right? But if we go to single slot, we don't even need that. So we can basically get rid of like committee shuffling and get rid of the whole swap or not stuff. And if we do that, then we could even have variable balances much more easily. So better variable balances would be nice. Also try to reduce incentives to join large pools as much as possible. Like these things could make it more viable to be a solo staker, and they could also make it more viable to have staking pools that are small instead of staking pools that are large, right? Like one thing that would be nice is, if you have a staking pool, you could make it possible for even a small pool to allow people to withdraw at any time if like you actually have partial deposits and withdrawals, and so the staking pool can also withdraw. So there are and potentially there's other things that we can do, right? There's a list of things that we could do, and aside from this, also keep it simple. Like, I do seriously think that this could be a significant simplification from the way proof of stake works today, right? Because, no more like end of epoch stuff, no more like intra epoch, saving a list, like saving these bit fields that we had to bother with an Altair, no more like really complicated interactions between LMD Ghost and like all of these things. No more swap or not shuffling. There's just a lot of things that just go away if we do something like this, and it would be so it would be nice to also like use this kind of opportunity to kind of a long-term simplify the Ethereum consensus layer as well. So that's what I have. Thank you.